light attendance this morning. Yeah. So, just a quick announcement. I've updated the solutions on Moodle, so there's now solutions all the way up to chapter 4, at the end of chapter 4. And we're just going to go on and make a start on chapter 5 this morning. So just, it's been a while. It was last Monday was the last lecture, so it's been a while. So just do a quick recap on where we are. We have the definition of congruence. This is what we found out was an equivalence relation amongst integers. So congruence mod n, a whole bunch of different relations for each modulus. The definition of this was if and only if n divides a minus b. This was the definition. So this was an equivalence relation on the integers. And any equivalence relation, remember we discussed the link between equivalence relations and partitions. So an equivalence relation produces a partition. And this partition Z as, and then we normally put a subscript n, so this is Zn, this is the integers modulo n, and this consists of the set of congruence classes. So every congruence class, so you take the congruence class of each integer, and you look at this. And of course, these will mostly, there's an infinite number of choices of representative integer, but you're only going to get a finite number of equivalence classes. So the definition of this notation is this is the set of every integer x that is congruent to A. And it turns out, because of the link between congruence and small remainders, you can produce a standard set of representative for these as the small positive remainders 0 through n minus 1. So this system, this is the integers mod n. Yes?
The colon.
Yes, so sometimes people use colon equals if you're supplying a definition. Yeah? So colon equals just means defining the thing on the left. The thing on the left. I often stutter when I speak, but I don't often stutter when I write. We've also discovered that you could apply the operation of addition onto your equivalence classes using the nice definition that to add two equivalence classes is simply to take the equivalence class of the sum of their representatives. We had to prove that that was independent of the choice of representatives, which we did. We also looked at the system of multiplication on congruence classes, defined in the same way, similar way. We multiply congruence classes by taking representatives from each of the two, multiplying the integers, and looking at the congruence class where that product lives. And we proved these were well defined, meaning that, well, what if we took a different representative for the congruence class of A, different representative for the congruence class of B, we would still end up with this same congruence class here on the right. So that proves that they're well-defined operations. Then we took a slight pause and we defined what the group in general was. So we reminded you of the definition of a group that we met last year in Maths Fundamentals. The system Zn plus forms a group. We proved that with identity element the identity element was, of course, the congruence class of 0. That congruence class, when you add it to any other congruence class, leaves it unchanged. And the inverses were the negative congruence classes, or the congruence classes of a negative. But for a multiplicative group, we needed a potentially reduced system, well, a definitely reduced system. So if we want to form a group with the operation being multiplication, we can't take all the congruence classes. We can only take those congruence classes where the GCD of A with n is equal to 1. So it's only the congruence classes of those numbers that are co-prime to the modulus. Okay? So we needed a reduced system, as these are the only ones, the only congruence classes having multiplicative inverses. Meaning that there exists a congruence class B such that A times congruence class of B equals the identity element, which is the congruence class of 1, if and only if the GCD of A with n is 1. Okay? That's what we proved. And I think that's more or less where we left it last time. We proved the statement that there exists a congruence class, which is this is the multiplicative inverse for A, because when you multiply them together, you get 1. Get the identity element in the multiplicative sense. 1 is the identity element in the multiplicative sense. And that happens if and only if the GCD of A with n is 1. Okay. Just a really quick idea of something important that came up in the proof of that was to run the Euclidean algorithm. John's been mentioning this in his cryptography. Run the Euclidean algorithm on the pair A and n to find out that their greatest common divisor is 1 and that you have alpha A, a linear combination of the two numbers equal to 1. Remember, that's what you get from the Euclidean algorithm as well. And this number alpha will be a representative of A inverse. Okay, because you can see there that if you take this equation, 1 equals alpha A plus beta n, turn it into a congruence, take the modulo n of both sides, then you get what, because this is 0 modulo n, it's a multiple of n, then you're going to get 1 is equal to the product of these two congruence classes. So the Euclidean algorithm can be used as a way to find the alpha, to find the inverse of a given number. It's one of the ways we have of finding the multiplicative. Okay, so that's kind of where we left it last time. I don't think I had a chance to do too many examples. Did we look at the Z8 one? So we got a couple of examples. Remember, for a group, a nice way of seeing what's going on in a group, the group is small anyway, is to look at the Katie tables of the group. The Katie table is just the operation table, the multiplication table for a group. So here are two of the multiplicative modular groups. So you've got the integers mod 5 and the integers mod 8. Now 5 happens to be a prime, so all of the non-zero numbers less than 5 are going to be co-prime to 5. 0 isn't. 0 is divisible by 5, so the greatest common divisor of 0 and 5 is 5. So that gets omitted. The only things that are there then are the equivalence class, the congruence classes of 1, 2, 3, and 4. And for Z8, well, you're taking all the things co-prime to 8, so that is only 1, 3, 5, and 7. Okay? Because 2, 4, and 6, and 0, they all have a non-trivial common divisor of 8, so they get thrown out as well. You see here we're dropping the square brackets. Okay, strictly speaking, there should be square brackets around all of those integers, but it just becomes a chore to write them down at the time. So we dispense with the square brackets. But we must keep in mind that the objects we're dealing with are the congruence classes of the integers. So these are two groups of order 4. You notice that they are different as groups. You can kind of get an appreciation of that from the tables, because in the case of Z8, for every A in Z8, it's true that A squared is the identity. A squared is equal to 1. You can see that because the diagonal elements on the Cayley table are all 1. Whereas in the case of Z5, that's not the case. Okay, 2 squared is 4, which is not the identity element. Okay, 3 squared is 4, which is not the identity element. Okay, so they are different groups. Let's just do another example for the heck of it. Make sure everybody's on the same page. Which would be a nice example. Z12. Any questions before we launch it? Well, let's go into the example, and then we'll see if there's any questions just about the review up to now. So Z12, the multiplicative system, Z12. So this is going to have congruence classes for everything that's coprime to 12. 12 has factors of 3, has prime factors of 3 and 2, 3 and 4, and 3 and 2. So we must omit every even number and every multiple of 3. And just look at the ones that are remaining. So we do have 1, we don't have 2, we don't have 3, we don't have 4, we do have 5, we don't have 6, we do have 7, we don't have 8, we don't have 9, we don't have 10, we do have 11. I didn't do this example at 12. It turns out to have 4 elements again. That's interesting. I've dispensed with the square brackets here again. And in the table, we can just quickly put all products. Of course, multiplying by 1 is easy. Multiplying by 5. 5 by 5 is 25, which is, of course, 1. 5 by 11, well, you see 11 is also minus 1, so we can quickly see that multiplying 5 by minus 1 is minus 5, and minus 5 we know is 7. So I know that that's 7 there. And then the one remaining one, 5 times 7, that has to be the one that isn't listed yet, which is 11. But 5 by 7 is 35, 35 is 24, plus 11, so it's congruent to 11. Much lower, 24. 7 by 11, which is minus 1. So 7 by 1 is minus 7, which is 5. 7 by 7 can't be 7, so 7 by, switch one as well. 7 by 7 is 49, which is 1 bigger than 48, which is a multiple of 12, so that's congruent to 1. And this must be the remaining one, which is 11. And finally 11, well, multiplying by 11, 11 is minus 1. 12. So multiplying by 11 is the same as multiplying by minus 1. So it's just going to reverse the order of everything there in the column headings. So 11 by 5 is going to be 7, 11 by 7 is going to be 5, and 11 by 11 is going to be 1. Okay, we don't have to multiply 11 by 11 because we can recognize that 11 is congruent to minus 1. So 11 squared is going to be congruent to minus 1 squared, which we know to be 1. Okay. So that's what the group is. That's what the Cayley table of this group is. Okay. By inspection, we can see this is merely, well, not merely, but interestingly, a relabeling, an exact relabeling of the group for Z8. What do I mean by relabeling? Well, I mean, literally, if you take the elements of Z12 and the elements of Z8, well, 1 is 1 in both cases. We can send 5 to be the same as 3, 7 be the same as so 7 over here is going to be the same as 5 over there. And 11 over here is going to be the same as 7. Okay. So really, if you change all these numbers throughout this table to 1, 3, 5, and 7, of according to that labeling, it'll turn the one Cayley table into the Cayley table of the other. Okay? So this is an example of a group. See, that means that we really should regard these two groups as being essentially the same. They've got different elements, they've got different looking elements, but really as a system of a set with this operation on it, one is just exactly mimicking the other. Okay? It's just if you attach different names to the elements, you make the table of one look like the table of the other. Remember, there's no inherent meaning in any of these symbols. These are just well, there is, because if you interpret these as number of objects, that there is an inherent meaning. But when you abstract it and just look at the system of the elements together with the operation, the structure of the system, of the multiplicative system Z at 12, not the structure of the elements, but the structure of the system and how they interact with the multiplication, is exactly the same as how Z8 behaves. Okay? So this is an example of what's called a group isomorphism. Things like this, we study in detail things like this and look at the full ramifications of them in the third year group theory unit. Okay? And it's a general hard question in group theory. Given descriptions of two groups, how can you decide whether they're isomorphic or not, whether they're essentially the same or not? If you're given two groups of the same size, it becomes it's a non-trivial question to investigate the groups and be able to say with, in all cases, to be able to say whether or not the two groups are the same or not. It's actually quite a hard algorithmic problem in general. Okay, so that's kind of a quick review of that. Any questions? Okay. So, what did we do in the tutorials last week? Well, one of the things we looked at was a method of evaluating a to the power b modulo n when b was large. Okay, if b was a large number, and we actually looked at these nice ways that we could evaluate a to the power b mod n. And there was two methods. We could replace the base a with a simpler representative mod n. So if a was a number bigger than n, we could quickly replace a with whatever is congruent to modulo n, whatever small number is modulo n. And we could reduce the exponent b with knowledge of the cycle type, or the cycle length, what we call the cycle length of a mod n. So the cycle length of a mod n, so some of the examples we were doing were 2 to the power 50 mod 7. When we're looking to work out 2 to the 50 mod 7, we don't need to evaluate 2 to the power 50, which would take a lot of memory and computing power. We can instead, you see, because there aren't too many things modulo 7. There's only a finite number of things mod 7. Okay, here they are, 1, 2, 3, 4, 5, 6. These are the only things modulo 7. So look at what happens with powers of 2. Well, the first power of 2 is 1. 2 to the 0 is 1. Then you multiply by 2, you go to 2, which is 2 to the 1. You multiply by 2, you go to 4, which is 2 squared. Multiply by 2, you go to 8. But if you're working mod 7, 8 is same as 1. So you get back to 1 here when you go to 2 cubed. And if you keep on looking at higher and higher powers of 2, well, you never visit 3, 6, or 5, okay, because you're trapped on this red cycle here. Okay, so each of these edges is multiplying by 2, but when you arrive back at 1, it means you're just going to be forced to repeat the same cycle. Okay? So this had a cycle length of 3. So we reduce 50 modulo 3. Modulo the cycle length. So 50 is equal to, try this up, I'm not so good today. 3 times 16, wasn't it? Plus a remainder of 2. So that means in working out 2 to the power 50, you go 16 times around this cycle, you arrive back at 1 for the last time, and then you've just got 2 more steps to take. So you end up with 4. So 2 to the 50 is equal to 2 to the 3 to the 16 by 2 squared. That's just rules of indices for breaking down an exponent, or breaking down the powers when you have this representation of the exponent. But when you switch to a congruence, then this is congruent to 1 to the power 16 by 2 squared, 7. And so that's congruent to 4, 7. So, okay, well, so we looked at a number of examples of that type. Is there any outstanding questions about things like that? So you can see a general principle here, that if you take any element, general, consider the cycle of values of a to some power mod n. See, here are all the elements of there are all the elements of the integers modulo n. 0 is there as well, I guess, but only considering the multiplicative system. So when you look at powers of a inside the system, there's only a finite number of elements. So certainly, Zn is finite. So certainly, the sequence of powers a0, a1, a squared will have to repeat. Yeah, because you're looking at powers of a, and you're living in this system where there's only a finite number of elements. Okay, you can form an infinite number of powers, but if you're only in a universe with a finite number of elements, sooner or later you're going to have to come back to a value that you've visited before. Now, what we saw in all the examples was that the first repeat, well, what we saw in all our examples, but it's true in general, will always be with a to some power. Let's call it L for the crack, cycle length. A to the L being back to congruent to a to the 0 being congruent to 1 mod n. Okay. Now that's what we saw in all of the examples, but maybe it's not true in general. So we do maybe proof in general. So this is true, will always be. So we need a proof of this. And we could do it with a proof by contradiction. So we're claiming here that so this sequence of powers, it begins with 1, so it's a to the power 0. And then it goes off through some other values. And I'm claiming that the first time you ever repeat a value on the list is when you reach 1 again, with some power a to the L. But maybe, maybe you could go through a sequence of values like this. Go here, 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 and then maybe repeat, maybe the first repeat could happen back here, not back here at the element 1. So you get some kind of a tail and then a cycle. Well, what I'm claiming is that can't happen. It will have to go through a proper cycle. So you begin at 1, you go through a bunch of other elements, and the first time you repeat is when you arrive back at 1. That has to be true. Now, but why is that true? Because there are systems and operations where you do have behavior like this, where you kind of lead in tail, and then a cycle starts, which only goes back to some intermediate point in the tail. Okay? But that's not what happens with pairs of elements beginning at 1. You always do come back to 1. So we can prove this by contradiction. So suppose the first repeat is not at a to the L congruent to 1. So suppose that's not the case, i.e. we've got 2 integer values, both strictly bigger than 0, with a to the power I congruent to a to the power j okay, we can assume that j is the smaller one yeah, that's all we need. Well, what can we get from this? Well, see, that implies that a to the power I, see, if we multiply both sides, we do need in all of this, we do need to know that a is actually an element from the multiplicative group. So a does have a multiplicative inverse. Because to do this proof, I need to use the inverse. So we multiply both sides by the inverse of a to the power j, which is just a to the power minus j. But that implies that I've got a to the power I minus j congruent to 1 mod n. But that kind of contradicts ourselves, because now we've got, well, hang on. Now we have a repeat where, the first element a0 was 1, and this is also equal to a to the power I minus j. And I minus j, whatever it is, it's certainly less than I. But these I and j's were supposed to be the first repeat. The first time the sequence of powers repeats itself. But once we assume we've got some I and j which are strictly bigger than 0, so we're not talking about a first repeat like this where we're repeating back at 1. But if we're repeating back at something which isn't 1, we assume that, but then suddenly we find an earlier power that repeats at 1. So we're contradicting ourselves. But there's nothing wrong in my argument there from the assumption I made at the top. So that's a contradiction. We have a repeat that happens earlier. Earlier because I minus j, the time we get the repeat, is smaller than I. But we just suppose that that was not the case, that we didn't first repeat at 1. And now we find we do. So that's a contradiction. So these cycles of powers of elements they always have, so the cycles of powers of A, which is A0, A1, A squared, etc., always form a cycle, repeating for the first time with A to the L being back congruent to 1 mod n, back at the beginning. So A to the 0 is 1. This L is called a cycle for the moment. We'll call it. Refer to it as. So it's the number of steps around this cycle of values you take. So here we're depicting one with a cycle length of 4. Okay, A to the power of 4 is back to 1 here in this picture. A0, A1, A squared, A cubed, A4. Okay. And as we saw in the example of 2 to the 50, knowing this cycle length, knowing the cycle length allows us, as we saw in the example, to simplify A to the B mod n. Like in the example, we were using 2 to the 50 mod n, mod 7. Okay? And instead of the original exponent B, we choose a small representative. Choose a small representative of B modulo L, B modulo the cycle length. Let's call it B prime. So then this will be congruent to A to the B prime mod n. The B prime is much smaller than B. If B started out being large, we'd expect B prime to be much smaller, and we've got a simpler evaluation to do. One that can be done with less computer memory, less computing power, less computing time. Here we found the cycle length was 3, so we went to 2 to the power of 50 modulo 3, mod 7, and we found that was 2 to the 2 mod 7, which was 4 mod 7. Calculating 2 squared is a lot more cheaper to do than calculating 2 to the power 50. So there's a general question. Given A from the multiplicative system, what is its cycle length? Now that's kind of a hard question. But we can get quickly at, we can get partial knowledge of the cycle length fairly quickly. So it turns out, and these will be things we'll be proving, it turns out that the cycle length will always be a divisor of this quantity, which is the size of the multiplicative group. Okay, is there anything you can't read there?
What's that? Sorry.
So, general question, given an A in one of these systems, what is its cycle length? That's a general question. Now we can answer it for the case of 2, we just draw out cards 2. But if the numbers get big, you know, we need some systematic way of addressing it. And it turns out that the cycle length L will always be a divisor of Zn, of the size of Zn. Yeah, so the modulus of Zn equals the number of elements number of elements in Zn, i.e. it's equal to the number of a's between 1 and n, between 1 and n minus 1, with the GCD of a and n being 1, okay? Because that's the membership criteria for being in Zn. Because this quantity is so important, because it restricts the possible cycle lengths, it's an important number to know about. And this is called, well, so we actually create a function called phi, and this is called the Euler Totient function. So phi of n is the size of the multiplicative system modulo. It's the number of elements in it. So it is also the number of integers between 1 and n minus 1 that are co-prime to n. Okay, so that's the definition for membership of this. So this is the subject of the next chapter. So even if we know L, even if we don't know L, the cycle length of A, we can always break down the modulus, break down the exponent b of a to the power b. We can break it down modulo modulo phi of n. Okay? Because phi of n will be a multiple of the cycle length. So we know that if we take a to the power of phi of n, that will represent a sequence of powers of a that go a number of times around the cycle, exactly, and also finish back at 1. Okay? So if that means we can also reduce the exponent modulo this number. Okay? However many extra steps you have to take after a multiple of phi of n to get the exponent b, that will allow you to evaluate a to the power modulo, a to the power b modulo n. Okay. So this brings us on to chapter 5, which is all about phi. We can start to look at a sequence of values of phi. Let's disregard phi 1, but phi of n in the multiplicative system modulo 2, there's only one element, which is 1. Multiplicative system modulo 3, there's 2 elements. Multiplicative system modulo 4, there's 2 elements. Modulo 5, there's 4 elements. Modulo 6, got 1, not 2, not 3, not 4, just got 1 and 5, so you're back down to 2 again. 7, there's 6. 8, we found there was 4. 9, there'll be 1, 2, 4, 5, not 6, 7, 8, so 6. So it's got a whole bunch of values like this. And phi 1 might be defined as 1, I think, just for convention, but that's only just a matter of convention, just to make some formulas work. You can get the computer to draw us some nice graphs of all the values of phi then. space after that. No. So Sage has the Euler Totient function predefined in it as a function. Just waiting for the tab completions to load. Here it is. Euler phi. I think we can. It's got its own plot routine. Oh dear. Join equals false. We don't want the lines joining the dots. Or it's a function on integers, so it's only defined at integer values. That's a nice picture. So this is showing you the value of phi then. The height of the dot is the value of phi then for loads of arguments there. But we threw down the first few values in a table there on the page a moment ago. But you can see it behaves quite wildly. So in a range of values around 800, you've got phi values of approximately, lowest it goes is maybe 160, all the way up to near on 800. Okay. And that behavior kind of continues. If you look at 10,000, shrinking a little bit. 0.7. Okay, even out at around 10,000, we're seeing a low value at maybe around just under 2,000 and up to a maximum value of around 10,000. Okay, so it's a function that's kind of wildly changing all the time. But there definitely seems to be some systematic behavior. It seems to be caught in a kind of a fan shape. This fan seems to be proceeding linearly as n goes out. So there seems to be some strict upper bound beyond which it can never go, which is a line. And there maybe is kind of some kind of lower bound beyond, lower than which it can't go, but that's maybe less certain there, because doesn't seem to be a firm line at the bottom. There definitely seems to be a firm boundary, linear boundary at the top. So the question is, can we understand the function phi? And can we calculate it easily? Because it gives us a multiple of the cycle length. And knowing the cycle length or a multiple of it is enough, or it gives you something that you can simplify large powers of an element in the multiplicative system. Okay? So the general problem here is phi of n equals what? Is there a good way to calculate phi? Well, there kind of is. Okay? So theorem 5.1, which is the main goal of this chapter, gives us simple enough formula for n, for phi then. So from the fundamental theorem of arithmetic, we know every integer factors into a product of primes. So suppose that's the prime factorization of n. Prime factorization of n. Recognize that thing. Then the value of phi then can be expressed really nicely in this, from this form. It's nearly a prime factorization formula, has got a lot of primes in it. And the rule is we reduce the exponent on each of the primes that we're dividing in, that we're part of n. We reduce the value of the exponent by 1, and we get a new factor added in, which is 1 less than the prime PI. So this isn't quite a prime factorization for phi of n. It has a bunch of prime factors here, but there are also these even numbers coming in, which is 1 less than each of the primes involved in the prime factorization of n. Okay. So a special case is phi of a prime number. A prime number p, well, what's the prime factorization of p? The prime factorization of p is simply p. So it is a prime number. So if you apply this formula here, well, you have to take p to the power, well, the exponent here is 1. So you take p to the power of 1 minus 1, so p to the power of 0. So this bit just gives you a factor of 1. So then the only thing remaining is just p minus 1. Okay. So the claim about phi of n always being a multiple of the cycle length that the powers of any element undergoes when you raise it to powers inside the group set n, this will lead to a result, a famous result, which is called Fermat's little theorem. Not Fermat's last theorem, Fermat's little theorem. And Fermat's little theorem says that if A is an element of the multiplicative system ZP, i.e. if the GCD of A and P is 1, that just means, let me just unravel that another bit, i.e. P does not divide A. So A is not a multiple of P. That means its congruence class mod P is an element of the multiplicative system. This implies that A to the power P minus 1 is congruent to 1 modulo P. Because this is the phi value, phi of P. And if we take what I said back here, we have to prove this, but sorry, this statement here. It turns out that the cycle length L is always a divisor of the size of Zn. So the size of Zn is a multiple of the cycle length. Well, if this number is a multiple of the cycle length of A, that means A to that power will be back at 1. Because A has its own cycle length, A to the L equals 1. But here we're raising it to a power which will turn out to be, but that is a multiple of the cycle. So A to this power P minus 1 might be running through the cycle a certain number of times, but it will come back to 1 at the end. So this means that automatically now, once we prove these things, we'll know that if we want to work out A to any large power modulo P, we can always reduce the exponent modulo P minus 1. Because the P minus 1th power is trivial. Brings you back to 1. Okay, so tomorrow we're going to start proving things. We'll prove Fermat's little theorem, and we'll start working our way towards a proof of this multiplicative formula. We call this thing the multiplicative formula for phi. Okay, thanks for your attention, and I'll see you tomorrow afternoon.